In this lecture, we're going to look behind the scenes to see what a program like MATLAB is doing when it computes something like the line of best fit. So in particular, those programs use an algorithm called least squares, and that's what we're going to work through today. Imagine you're in the scenario on the left, and you have these data points, and they all live perfectly on that straight line. If you needed to find the slope and y-intercept in order to write down the formula for that line, you would just need to take any two, compute the slope between them, and then use something like point-slope form in order to write down the explicit line. If you look at this data set on the right, you just imagine here that you have a huge set of data, and looking at it, it looks like there's a line pattern there. So we would like to say whatever the results of this experiment are, it seems linear in nature. But how do we work out what the slope and y-intercept should be? So there is a methodology here, it's called least squares, and we're going to look in particular at the least squares method for a straight line, and then we'll just say this formula that we have generalizes for polynomials. We'll need some math concepts from linear algebra. If you're familiar with all of the bullet points on this slide, you can go ahead and skip forwards. Otherwise, let's take a minute just to work through the concepts of matrix multiplication. I'm not going to do like all of matrix multiplication, I just want to mention it. A test to detect when two vectors are perpendicular to each other. And then I'll mention the definition of the matrix transpose. So matrix multiplication makes sense when you have two matrices. Say I'm going to call the left one A, and I'll denote its coordinates like this. So that's A11 means first row, first column. AN1 means nth row, first column. Then I'm going to go to the right and say that we stayed on the first row, but now we're in the mth column. Kind of fill out this matrix. And then down here, we're on the nth row, mth column, if you understand what I'm saying there. So this is an n by m matrix. It has n rows and m columns. We can multiply that by a matrix we'll think of as B, just for letters. So let's call this B11. And then we'll fill out the first column. And what's going to have to be true about B is it needs the same number of rows as A had columns. So in order for matrix multiplication to make sense here, I have to say I'm on the mth row, first column there. And then we can say we have perhaps P columns in B. Fill out the rest of this. So here we're in the mth place. Mth place, I think. I said that wrong. So this is an M by P matrix. Matrix multiplication only makes sense if their inner dimensions match. So M has to be M. Then you're probably familiar with this, but how we matrix multiply is we go along the rows of A and down the columns of E, and we pair those up in every possible way. Let me see if I can write the product kind of concisely. So the very first entry in the product would be the first row of A times the first column of B. And what we do is we multiply this entry times that one, plus the second entry in that row times the second entry in that column, all the way through the mth entry in this row. And it looks like I've got my indices switched there. Let me fix that. This always happens to me when I have too many indices. This should have been 1m. Okay, there we go. So we'll keep doing these pairwise products until we get to this entry meeting that entry, and we add all those pairwise products together. So I can write this as a sum. Products of the form A1k bk1 from k equals 1 through m. So that's the entry in the first row, first column of the product, and you can get that by looking at those outer counters. So you match these two together, it's the first row, first column. So if I wanted to write the first row, second column entry, it would be a very similar sum. I would sum from k equals 1 through m, a first row k, bk second column. So that would be like the first row of A times the second row of column, the same algorithm we just did. We've just shifted over one column in the B matrix. And we go all the way through the end of the first row. So that's going to be A1K BKP. Okay, and that would fill out the first row, and then we do that for all the rows until we get down to the final row. Same idea, k equals 1 through m. Now we're going to be on the nth row of A, so it's going to be ANK BK1. The sum of those pairwise products would give us the nth row first column. Again, you look at these outer counters there. That should be n, 1. The second entry in that final row would be the sum from k equals 1 through m of ANK BK2. And we keep doing that until we get all the way to the final entry in our matrix, which is going to be a sum from k equals 1 through m of ANK BKP. We're not actually going to multiply out any matrices by hand in this lecture, although there will be matrix multiplication happening at the end when we get to the least squares formula. While we're trying to understand what the technology does for us, like if I'm going to ask MATLAB to give me the coefficients of the line of best fit, I'd like to know where those came from. I'm still going to rely on, say, MATLAB to do explicit matrix multiplication for me because this algorithm I already know and understand. So I don't need to necessarily do this by hand if I can let technology do the work for me. Okay, how do you detect if two vectors are perpendicular? This is our next math topic that we need to review. So say I have these two vectors, u and v. Are they perpendicular? So is the smaller of the two angles that we open up between them equal to 90 degrees? Dimensionally, we need to think of these as columns. So let's say u has coordinates u1 through un, and v has coordinates that look the same but with v, so v1 through vn. We have a really nice test for when two vectors are perpendicular. We say that u is perpendicular to v exactly when what we call their dot product is 0. If you've seen that before, great. If you haven't, let me define it for you. So where u dot v is the sum of their pairwise products. So that's u1 v1 plus u2 v2 all the way through un vn. So that's always going to give you a number, and if and only if that number is 0, can you say that those two vectors are perpendicular. Okay, the last thing I want to mention is what a matrix transpose is, and I'm going to also tie this into another way of writing the dot product so that actually we have kind of an algebraic maneuver between the two concepts. Okay, so if A is up here at the top the way I've defined it, the transpose of A is just going to be the flip of A. So what were rows become columns, and what were columns become rows. So in particular, A transpose would be, let's see, what I called A11 through A1M on the first row needs to become the first column. And then what I called AN1 through ANM on the final row, that needs to be the final column. So that's going to be AN1 all the way through ANM. You can see the dimensions flip, so it's going to be an M by N matrix with M rows and N columns. You can check this on your own. It's just algebra, just comes out of the definition of matrix products and also the dot product above. U dot V is equal to U transpose times V. So this is a matrix product where instead of thinking of these as vectors, I'm thinking of U as a n by 1 matrix so that U transpose is 1 by n, and then V is still an n by 1 matrix, so their product overall is just going to have one component. It's just going to be a number. So that means that U and V are perpendicular when U transpose V is 0. And then another thing I'll let you check is if you take a product of any two arrays where their product makes sense. So if we take A and B up above and transpose it, a little bit of work to show that that would have to be B transpose A transpose. Key concept here is the order. So you flip the order, transpose each. Why is the order so important? Because matrix multiplication in general is not commutative. There's one more matrix concept that I should mention before we dive into the least squares algorithm, and that's the concept of a matrix inverse. Not every matrix has an inverse. For one thing, a matrix must be square. So if A is an n by n matrix, so any square matrix, 2 by 2, 6 by 6, what have you, and the matrix equation A times some vector x equals some vector y, if this equation has a solution for any choice of right-hand side y, then we say A is an invertible matrix. This means that there exists an n by n matrix, which we denote by A inverse, so that for any, let's call it vector u, some n by 1 vector u, the matrix product A inverse times u returns u, as does the product A inverse A u, that also returns u. What this means is if I go back to my general equation at the top, ax equals y, we can now solve for the solution x to this equation. By multiplying both sides of this equation by A inverse from the left, we can write x equals A inverse AX, but then that equals A inverse y. We're going to see this appear at the end of the derivation for the least squares formula. Now that we've gone through those linear algebra concepts, let's return to the context. We're trying to fit lines through collections of data. In particular, given ultimately a set of data which doesn't live perfectly on a line, we want to justify our notion of a line of best fit. Okay, so suppose I'm looking first at this perfect data set, where I have, say, this point right here is some measurement x1, y1, like at time t equals x1, measured quantity y equals y1. And then let's say we have n of them, so this would be xn, yn. So I have all these data pairs, and it so happens that they all live perfectly on a line. The line is y equals m1 plus m2x. A little bit of a strange order here compared to how you often write down a line, but the idea is we're going to write these in ascending powers of x. So since this line perfectly fits through this data, that means if I take any of these data points and plug in the xi value on the right where I have x in the equation and plug in the corresponding measured yi value on the left, it would be a true statement. So now I'm going to take this equation and reinterpret it in terms of these data points, where instead of having just this general variable x and general variable y, I'm going to specifically think about my data. So in particular, we have y1 equals m1 plus m2x, that's like our first x1, that's our first data point on the line. Then the second one we could think of as plugging the y2 value into this equation and getting y2 equals m1 plus m2x2. And then we keep doing that all the way through yn equals m1 plus m2xn. We have a system of n equations, so we can organize these as, say, a list of entries in a vector. So let me have y1, y2 through yn as the coordinates in a vector. And on the right, I'll start off with one vector and then we'll split them up. So this will be m1 plus m2x1, m1 plus m2x2, all the way through m1 plus m2xn. Okay, I'm out of room. I didn't organize this slide very well. So let me now take this and we'll continue over in the top right. So I can take that big vector on the right and split it up. The way vector addition works, you just add coordinate by coordinate. So I could write this as the vector m1, m1, all the way through m1 plus the rest of it, so m2x1, m2x2 all the way down to m2xn. You can pull these scalars m1 and m2, these numbers, out in front of the vectors and think of this as the number m1, that's the y-intercept of the line that we're looking at, times the vector of all ones, so 1, 1, all the way through, 1, plus the number m2, which is actually the slope of our line, times the vector x1, x2, all the way through xn. Essentially, I'm just plugging these vectors into the equation that we have at the top, but now I'm going to do something a little bit more than just repeating this equation, but in vector form. You can check that this is actually an alternative way of organizing the information that you would get from a matrix product. So this is where matrix multiplication is going to start to enter into the story. So how does this work? If we take the matrix whose columns are the first column of all ones, and then x1, x2, all the way through xn, and multiply it by the vector, which is 2 entries, m1, m2, then I claim we get this. Now that we've brought our data points into our line equation and we've reorganized it as a matrix calculation, where over on the left I have this vector of y entries all the way over to this matrix times the y-intercept and slope, let's go to a new slide where I'm just going to have this, and we'll apply this setup to a problem where our data fits perfectly on a line. All right, let's identify the components that we have in this matrix equation at the top that we looked at on the previous slide for this data set here. We are beginning here with 3 data points which actually do live perfectly on some lines. This is not a very realistic or useful set of data, but how do we take this information, translate it into this equation, and then solve it? In this case, we'll actually solve it quickly numerically because there actually is a slope and y-intercept which will perfectly cause the line to pass through the points, but we'll get there when we get there. So first, let's arrange the matrix on the left, the matrix on the right, then we'll discuss how to solve for m1 and m2, where m1 is the y-intercept and m2 is the slope. Let's create some shorter names for these objects. So how about this matrix with 2 columns? We'll call this matrix A. This unknown vector of an intercept and a slope, let's call this m. The coordinates of m are what we want because that's going to give us our line. And then this vector on the right, let's call this y. So we have a matrix times a vector equals another vector. You can check your dimensions here. This is an n-row 2-column matrix. This is a 2-row 1-column matrix. So the inner dimensions match. And after multiplication, the result will be an n times 1 vector with n rows and 1 column. If you're wondering what n is, little n here is the number of data points. So if we have n data points, we would organize them as x1, y1, x2, y2, all the way through xn, yn. So that's what n is. All right, so in this problem, we have 3 data points. So A will be 3 by 2. So in particular, A is going to be a matrix where the first column is 1, 1, 1. And the second column is x1, x2, x3. So if you look at the x coordinates of our data points, that's going to be 1, 3, 4. M is unknown. M is ultimately what we're solving for, so we can't write it down yet. Y is going to be 3 by 1. And in particular, here it's the vector of y measurements. So that's going to be 1.2, 1.6, 1.8. So then we want m1 and m2 so that our matrix equation is true. I've written this in the matrix form. If we actually translate it back into the form that we started with, so let me go back just for a second, where we took our line equation and we plugged in our data points, what would that look like if we'd taken that point of view on this problem? It would mean that m1 plus m2 equals 1.2. but also m1 plus 3m2 equals 1.6. And lastly, m1 plus 4m2 equals 1.8. That's a system of 3 equations, or in general, n equations, for 2 unknowns. So this is what we call an overdetermined system. It's like we have more equations than we actually need, assuming that there is a solution. So if there are numbers m1 and m2 that make all 3 equations true, we could throw out the third one and just solve for our 2 unknowns using the first 2 equations. So you can do that by hand if you want to. Let me just show you in MATLAB how you can solve the system. So now I'm in MATLAB Online, and I'm going to set up a calculation in MATLAB which will solve for the unknowns m1 and m2 because they can be solved for in this problem. We actually do have a line that passes through those 3 data points. But even when we go to the more interesting case, where we have imperfect data and we're trying to fit a model to it, this will still be the same initial setup. So what we're going to do is make our matrix A. That's going to be 1, 1, and I'll just enter down for the next line, 1, 3, 1, 4. You can run this and you can see it in the command window if you want, and then you can suppress the output. There's no point typing in a matrix M of unknowns. We don't know that. So the next thing would be Y, which is going to be 1.2, 1.6, 1.8. I chose to put new rows on new lines, but you could also use the semicolon. Like you could put these on the same line and just separate rows with semicolons. Okay, what we've done so far we'll do again later. So we'll always have the matrix A and the vector Y. In this particular case, if AM equals Y actually has a solution, then MATLAB actually has a specific way for you to solve this. So this is distinctive to MATLAB, but it's called left division. Right? You don't left divide a vector by a matrix on paper, but in MATLAB that makes sense. So this is called left division. It's a MATLAB thing. The result that we have here are the coordinates m1, so m1 equals 1, and m2 equals 0.2. Let's go back to the slide. So if there is a solution, then option 1 is just solve for it by hand. If there's a solution, then this yields a system of equations which gives you the solution. So you could just solve it by hand, or if you have another way of solving this kind of problem, you can use that other way, Excel, whatever you want. In MATLAB, it would be left division. So MATLAB's left division gave us 1 and 0.2. That means our line of best fit is y equals 1 plus 0.2x. In other words, a y-intercept of 1 and a slope of 0.2. Realistically, if you're talking about least squares, you're not going to have a solution to that system. So you might have a system here, but one of your data points lives up here, and there's no solution. So if not, we do least squares. The good news is that you don't really need to make a judgment call here. This whole example can now be thrown away because if I tried to solve this problem using least squares, I'm still going to get 1 and 0.2. So by default, we use least squares. Now let's take a look at what the least squares process involves. So first we're going to set this up kind of visually, geometrically, and then we'll get into the algebra. So this is the system of equations that we're considering written in matrix form. We've already discussed how the left-hand side, that matrix times that vector, could be thought of as m1 times the vector of all ones plus m2 times the vector of x coordinates. Let me call this vector u and this vector v. So what I have here is a number times u plus a number times v. This system of equations yields a solution, a curve which perfectly fits through the data, if our measured data y can be viewed as a number times u plus a number times v. So if y equals m1u plus m2v for some values of m1 and m2. This is called a linear combination of the vectors u and v, and we can visualize what it would look like. These vectors actually live in n-dimensional space, but I don't need to be working in n-dimensional space to sketch the picture. Let's suppose that this is u, and this is v. Even in n-dimensional space, all of the ways to take those vectors, multiply them by numbers, and add them together produces a plane, just like the tabletop that you might be working on. Let me call this plane P. Plane P contains the possibility of, say, y equals 0. You would get to that value by just taking m1 and m2 to both be 0. This would be like the vector with n zeros in it. Any other way to take u and v and multiply them and add them together is going to send you somewhere in this plane. So we can also say that this system of equations would have a solution if the vector y lives on the plane P. Okay, I'm going to copy this plane over to the next slide, and we'll talk about what happens if y doesn't live on P. So what if we're looking at data which won't live perfectly on a polynomial, but we would still like to fit a polynomial to it? Okay, so here's the plane P and the vectors u and v from before. What we want to imagine now is that our vector y of measured data is not a combination of the columns of A. So it can't be graphed as lying flat on this plane. If I wanted to graph it, I could kind of graph it as sticking up out of the plane at some angle. Hard to do this on a flat screen, but this is a three-dimensional picture. Hopefully you can imagine that this is kind of like coming out of the plane like that. In particular, it's going to cast this shadow on the plane. It's like if I drop the altitude straight down from the end of y to this plane, we can form a right triangle. So this is our vector y. Okay, I'm calling y specifically the vector of measured data. So let me get rid of this y equals 0 down here. That's a little bit confusing. I just wanted to point out that the origin does live on this plane, the origin in n-dimensional space. But let's get rid of that. We don't really need it. What we're trying to do ultimately is find the vector on P, which is closest to the vector y. In other words, if I measure the distance from that vector to y, this distance is smallest. Let's give the altitude that I've drawn a special name. We'll call it r hat. This altitude is going to minimize that distance. That's a geometric argument. Let me just sketch an example of what it would look like if we didn't minimize the distance. So in particular, suppose I choose some other vector which lives on this plane. This is not going to be the vector that's closest to y. I don't have a good name for this vector, but what I know is that it's some linear combination of the columns of A. So we could describe this vector as c1u plus c2v, where that's just any pair of numbers c1 and c2. So how close is our vector of measured data y to this new vector I've sketched on the plane? It would be the length of this vector Let me just call that vector s. I don't think I need an s anywhere. So for any pair of coordinates c1 and c2, it gives us a new vector on this plane. And then how close is that vector to y turns into the length of the vector that we could sketch that connects the head of the vector on the plane to the head of y. So let's set this notion of measuring y against vectors, let's set it up precisely with coordinates. Any vector on the plane can be written as c1u plus c2v for the right choice of coordinates c1 and c2. c1u plus c2v, as we've seen, is equivalent to the matrix product A times the coordinate vector c1, c2. For just a generic coordinate vector c1, c2, let's call that vector c. So this is like A times some vector c. We want to minimize the length of the vector we could describe as s equals y minus ac. And then we won't go through the proof of it, but you can probably believe it just because the r vector I've drawn is the altitude straight down from y to the plane. But this length is minimized when the c vector is not a generic c, but the actual vector m of coordinates that we're looking for. And as a result, that distance vector that we're sketching is the vector I've labeled as r. Let me actually call this m hat just to match r hat. So we're talking about a special configuration here. So in particular, am hat is this vector on the plane that we're thinking of as closest to y. So that's that leg of that right triangle down on the plane. Now this is a statement about r, and that's great. But ultimately, what we're trying to find with our least squares computation is the vector m. So let's rearrange the terms in this, and then we'll go on to the next page. So what we're really looking for is m, so that am equals y minus this vector r. And at this point, it might seem like I'm just going in circles because I've written down one equation with two quantities that we don't currently know, r and m. But we're going to use the fact now that r is perpendicular to the plane. It's sticking straight out of the plane in order to come up with a way to ultimately solve for these coordinates m that we need for our line of best fit. Okay, so let's finish our derivation for the coordinates of the line of best fit. Where we left off, we had identified a vector r that was perpendicular to the plane. So what that means is if I take any vector on the plane, we can describe it as AC. So this is like any vector on the plane. Since r is perpendicular to the plane, any vector on the plane, written in the form AC, dot r equals 0. So on the left-hand side, we have our vector dot product. And as we mentioned earlier, it turns out two vectors are perpendicular if and only if their dot product is 0. So since y is perpendicular to everything on the plane, this vector dot product must be 0 for any choice of coordinates c1 and c2. Now we're going to use some of those other matrix facts from earlier. So currently we have 0 equals AC dot r, where this is a vector dot product. We discussed how taking the dot product of two vectors is equivalent to taking a matrix product of two vectors if you've transposed the first one. So I'm just going to write the exact same computation in a different way. This is equivalent to AC transpose times r. AC was a column, so AC transpose is a row. R is a column, so when you do this matrix product, you get a row times a column, and it gives you the sum of the same pairwise products. Okay, but we mentioned a property of matrix transpose, which said that the transpose of a product is the product of the transposes, but in reverse order. So this is going to be the vector C transpose times the matrix A transpose times R. That's all a matrix product. But now I'm going to use associativity and essentially group the latter two terms together and think of this as C transpose times A transpose R. A transpose is 2 by n. R is n by 1. So overall, A transpose R is a 2 by 1 vector. C is also a 2 by 1 vector, so now I have a row times a column. So we could take this product and convert it back into dot product form by untransposing C, if you will. So this is going to be the vector C dot the vector A transpose R. So now I've put this back as a dot product. We've identified that A transpose R is just a 2 by 1 vector. Let's call it W. And its coordinates we'll just call W1, W2, whatever they are. This statement now that C dot W gives us 0 is true for any choice of 2 by 1 vector C. So it's also true if I plug in W in that first vector. So let's now identify that we've set W equal to A transpose R, and what we're going to do is plug W in for C. So we get 0 equals W dot W. So the first copy is us plugging W in for C, and then the second copy is just the definition of W. But you take the dot product of W with itself, and what you're going to get is W1 squared plus W2 squared. Those are non-negative numbers, so if W1 squared plus W2 squared equals 0, both W1 and W2 have to be 0. So now we've concluded that A transpose times this perpendicular vector that's minimizing our computation is 0. Okay, we've gotten a bit off track doing some matrix computation, so let's pull it back to what we were doing originally. What we wanted was a vector m hat, so that A times m hat equals y minus this perpendicular vector r. We didn't have r, we didn't have m, we just had this one equation, but now we have a really neat fact about r that we're going to use. So let's take this equation and multiply the left-hand side and the right-hand side from the left by the matrix A transpose. So I'm just going to do A transpose on the left, A m hat, equals A transpose on the left times the vector subtraction y minus r hat. Now on the right-hand side of the equation, we can distribute the A transpose matrix, so that's going to be A transpose y minus A transpose r hat. That second term is 0. That was the whole point, really, of the calculation we just did, is now we can get rid of r from this equation, and we're just left with something to do with y on the right-hand side, A transpose y. Go ahead and compute the dimensions of A transpose A. So what kind of matrix is that? Well, A transpose is 2 by n. A is n by 2, so overall this is a 2 by 2 square matrix. This square matrix that we're looking at now could be invertible, and in most cases it will be. That means in this equation, A transpose A times m equals A transpose y. We can now invert A transpose A to solve for m. We get the resulting least squares formula for the coefficients of the line of best fit. We say m hat equals A transpose A inverse times A transpose times y. Notice one nice thing about this formula is that it's entirely in terms of A and y. And that's great because y is the collection of dependent measurements that we had from the start, and then A is a matrix that we wrote down at the start. So at the end of the day, we end up with this kind of lengthy formula, but you just say it a few times and you have it memorized. And all we need for it is the matrix A and the vector y. If you were to do this by hand, it would be a nightmare because you have a matrix product. So first you have to do the matrix multiplication, then you'd have to invert that and then multiply that by another matrix A transpose and then multiply that onto the y vector. But luckily we can do this really quickly in MATLAB. So here's the matrix A and the vector y that we already saw for that problem we did at the beginning where we had 3 points which lived perfectly on a line. So we already found the vector m with the y-intercept and slope that would fit this data, so let's now use the least squares formula. The main thing to know in MATLAB is how to type in the matrix inverse and the transpose. For inverse, it's going to be inva of something. And then transpose is actually prime. It's like a single apostrophe in MATLAB. Matrix multiplication needs just plain old star. So A transpose A inverse, you're going to do inva of A transpose star A, and then star A transpose star Y. We run this, and we get the same coefficients as before. The y-intercept is 1, and the slope is 0.2. Now that we've gone through the derivation of least squares, if you wanted to do the least squares calculation, you would just set this up. So you just jump straight to this formula. The derivation we just did was set up for a line, but it turns out that formula generalizes to higher degree polynomials. The formula itself is the same. The only thing that's going to be different is the matrix A. So I'll show you how to set this up. Here we have 4 data points, and they look, just based on the 4 that we have, kind of like a parabola. So let's set up the least squares calculation in order to find the coefficients for the best fitting quadratic 2 polynomial. Just like before, we're going to order the coefficients in ascending powers of x. So what we want is m1, m2, and m3. So I'll say we want a vector m whose coordinates are m1, m2, and m3, so that y equals m1 as a constant term plus m2x plus m3x squared. So we're picking up an extra term over here, which is going to look like m3 times the square of the x data. How that changes our matrix A is when I set up A, the first 2 columns are going to look the same as before. So let's see, here I have 4 data points. So n equals 4. That's the number of data points. So for my first column of A, it's going to be 1, 1, 1, 1. The second column is going to be x1, x2, x3, x4. So that we get from looking at the first coordinate of each of these data points. So it's going to be 1, 2, 3, 4. Those are the x coordinates that we have. And then the next column is going to be those x values squared. So that's what happens with this third piece over here. So my third column is 1 squared, 2 squared, 3 squared, 4 squared. Y is the same as before. So y is going to be a vector with 4 entries in it, and it's going to be the y coordinates. So 1, 7, 9, and 3. And then just like before, the coordinates for our parabola of best fit are going to come from doing A transpose A inverse A transpose Y. Same formula as before. Let me set this up and solve it in MATLAB. Okay, so I'm going to take the same formula as before. I just need to adjust what the matrix A really looks like. So 1, 1, 1. That's my first row. 1, 2, 4. 1, 3, 9. And then 1, 4, 16. The 1, 2, 3, 4, it's kind of unfortunate numbers actually, but those were the x coordinates. So x coordinates might not look so nice all the time. And then my y vector, I'll write it as a row. So 1 semicolon 7 semicolon 9 semicolon 3. And then same formula as before. So I run it. And we get that the coordinates we need are -12, 15.8, and -3. So this is the constant coefficient. This is on the x term, and then -3 is the coefficient in front of the x squared term. If you're curious how this compares to asking MATLAB directly for the coefficients of the degree 2 polynomial of best fit, it's going to be the same. So if I do polyfit, I have to give it the x data, so 1, 2, 3, 4, comma the y data, so that's x data, comma y data, comma the degree of the polynomial you want. It gives us the same numbers, but in the opposite order because it orders it in terms of the x squared term first, so just be careful there. Okay, so this calculation we did in MATLAB gives us the coefficients. I've plotted the parabola here. You could always graph that in MATLAB at this point if you wanted to. So our best fitting parabola is y equals -3x squared plus 15.8x minus 12. We're going to stop this first look at least squares here, and the next lecture we'll take this a little bit further. We'll look at how to compute the residuals, and we'll also look at some alterations that you can make to the matrix A in order to get exactly the type of model that you're looking for.